So a good place to start a course on time series analysis is with a description of, well, what kind of data are we going to be analyzing? Simply put, we're going to be observing data over time in a series, you could say. So for example, maybe we observe, let's say, your weight on January 1st, then January 2nd, January 3rd, and maybe all throughout the entire year. And so we have a series of weights, and we would like to analyze that. Alternatively, maybe we have the weight of a cow, or maybe the height of a plant. Again, every single day we collect information on the height of the plant. Now, another area where time series analysis or time series data comes about is in financial situations, such as, let's say, your stock price. A stock price on January 1st, a stock price, that same stock on January 2nd, same stock price on January 3rd, and so on. There's other kinds of financial or business-related data as well. Maybe, for example, well, how many customers does Starbucks have on January 1st at a particular location? How many customers on January 2nd? How many customers on January 3rd at that same location? So again, we have a series of data observations collected over time. Excuse me. Now, if we get away from, let's say, daily observations, maybe we think of quarterly or yearly, there's a lot of time series data that come about through, you could say, data that the government has collected, such as maybe the gross domestic product, or GDP, for a particular country. We often see that as a quarterly value. You could also look at, let's say, unemployment rate quarterly as well. So there's many different places where time series data comes about. The key is the data is a series collected over time. And what makes time series data unique, and why typically it doesn't fit well into most statistics courses as maybe like a subtopic, is that we have this dependence of observations over time, meaning, let's say, your weight on, let's say, January 2nd is probably going to be somewhat dependent upon what your weight was on January 1st. Your weight, let's say, on January 3rd is going to be dependent on January 2nd, and maybe also somewhat for January 1st as well. So we have, we don't have independent observations. We have dependent observations. And one can't just, let's say, handle this dependence how you would maybe in other courses where, maybe you have, if you're familiar with generalizing linear mixed models, where you could have a particular term in your data set, or I'm sorry, in your model that helps account for that dependence. Typically, one cannot do that in these kinds of situations. And so in this course, what we will learn to do is first identify this dependence. There's a variety of different dependent structures that can occur. So we'll look at how to identify a corresponding structure. We're going to measure the amount of dependence, and then we're going to take advantage of that dependence to try to construct models that best estimate our corresponding variable that we're measuring. And then what I think is a really cool thing that we do in a time series analysis course is that we're going to now, with this model, forecast the future. In other words, so let's say you have your weights from January 1st through December 31st. Maybe you want to forecast, well, what is going to be the next January 1st? And so we take advantage of this dependence that we've observed over time. We've constructed a model to correspond to it. And now we can forecast future values. We could forecast, let's say, future plant heights. We could forecast future amounts of number of customers that are at a Starbucks location. We could forecast, let's say, GDP. We could forecast unemployment rate and so on. So in this course, we're going to try to forecast the future. Now, also in this course, we are mainly going to focus on one series, meaning, let's say, just one Starbucks location, rather than, let's say, looking at all Starbucks locations in a particular city. Maybe there's 5 different locations and you have the number of customers per day at each location. Typically in a time series analysis course, you don't talk about that too much because there's a lot that you need to do with just one series of data. In other words, you could say, let's say, one variable. Later in the course, we will see a little bit about how to deal with multiple time series data. But here we're going to focus typically on one time series. Also, we will typically not look at any explanatory variables that might help us understand our particular variable of interest. There will be a small section in our course where we do talk about that, but typically in a time series analysis course, you have one variable and you're looking at the dependence over time, trying to understand that dependence structure so you can come up with a model for it. Now, sometimes people coming into a time series course have a mistaken impression of what time series data or what our corresponding analysis, what we're going to actually do. And they confuse it with what's often referred to as longitudinal data. Now, for those of you who are not familiar with longitudinal data, basically longitudinal data is data that's collected over time as well. So for example, it might follow a similar situation like this that you typically see, like maybe in a clinical trial setting, where, let's say, for person or subject number 1 in a clinical trial, you observe some data on them at time 1, time 2, time 3, and time 4. Maybe just only 4 different time points. For subject number 2, you do exactly the same thing. Now, in this particular case, we would expect for subject number 1, these observations to be dependent on one another. For subject number 2, these observations dependent on one another, and so on. A common way then to take into account this dependence is to use a generalized linear mixed model, where you could have a term corresponding to subject to account for that dependence. That's not what we do in a time series analysis course. Instead, what we have is data, such as I illustrated here, where you have a long series of data that's collected over time. And we're looking at to model that series alone. Longitudinal data, typically, in most settings, you might have a short time series of data. Okay, so let's look at a little bit more detail some examples that we will be working with in this class, to give you a flavor or an idea of the kind of data and the kind of analyses that we're going to be doing. Also, these examples will help get you up to speed on typical things that we do with the data inside of R once we get it in terms of plotting. So this first example that we're going to look at is called the OSU Enrollment Data. So throughout my notes, you will see a typical style that I use, where I announce example, the name of the example, any R programs that we're going to be using corresponding to it, and then also a data set name. Now, this OSU Enrollment Data example is probably my most favorite example that I use in a time series course, because I was actually, you could say, somewhat involved in the situation that corresponding to this data. So my first job out of graduate school was as an assistant professor in the Department of Statistics at Oklahoma State University. When I was there, they had a problem where the administration forecasted too high what enrollment was going to be. Because there was less students there was then less tuition dollars, and thus the university had a budget deficit that they had to deal with. And so that made me interested in this example, because I was teaching time series analysis at the time. And so I went and actually talked to the people who were making these forecasts, and I got their corresponding data to see if I could do a better job at forecasting. And so here's what the data looks like. So they went back to fall 1989. OSU, Oklahoma State University, had an enrollment of 20,110. In the spring semester, in 1990, they had an enrollment of 19,128. It's not unusual to have a little bit lower enrollment in a spring semester because you have some students who graduate at the end of the fall, and you typically do not have any, or not many students start brand new in the spring. Then the summer 1990 enrollment was 7,553. Again, it's very typical to have lower enrollment in summer because not all the students are on campus anymore. Then, again, in our series of data collected over time, fall 1990 enrollment was now 19,591. And I have data all the way up to fall 2002, where enrollment was 22,992. Now, our variable is OSU enrollment. In a symbolic form, we can denote it as X. And then we're going to put a subscript associated with X to say, well, what time was this corresponding data collected? So X1 is going to correspond to our first observation, X2, the second observation, down to X40. So the subscript T here represents time. Okay, now let's take a look at this data. So this data is stored in a comma delimited file. That's why it's a .csv extension. And so I could actually open this up, let's say Notepad, and we can see the data set where the first row in the data set corresponds to the variable names, as you often see with most data sets nowadays. And each column in the data set is separated by a comma. Then underneath that first row, we have the actual data itself. And again, each data value is separated by a comma. That's why it's a comma delimited. Now, if I want to, on my computer, I can just simply left click on, I can just open up that data file, and what it normally would do is just simply open up into Excel. Excel works quite well with comma delimited files. Now this data set, and I forgot to mention this to you, this data set's available on my corresponding course website. So I download that data set, I put the data into a folder on my computer where I know it's located, and then I can then read in the data. So since it's comma delimited, I'm going to simply use the function read.csv, and I specify the file name, OSU underscore enroll.csv. Now, if you have not specified, if you have not indicated in R yet exactly where that folder is, where this file is located, you do need to do that. There's a number of different ways to do that. One is to use the function setwd, which stands for set working directory, and you can put the actual formal directory structure where your file is that you've downloaded. So I'm going to read in my data, and then I just include this extra argument here, strings as factors equal true. And the reason being is if you notice that we have this variable semester, which is non-numeric, and this just allows me to work with non-numerical variables a little bit easier. In R's terminology, it converts this non-numerical variable into what's called a factor, or you can think of it as a categorical variable. Okay, so I'm going to read in the data. I'm going to put it into an object called osu.enroll so I can save it and work with it. I'm going to use the head function to help me verify that I've read the data incorrectly. This is going to print the first 6 observations. And then the tail function is going to print the last 6 observations. So let me go ahead and run that code. And here we go. So indeed, I can go back to my original data set, the comma delimited file, and indeed see that everything read in correctly. So that's good. So let me pop back over here to Word. Now let's talk about doing a plot. We're going to look at a few different ways to do these plots in R. Typically, whenever you get a time series data set, this is after you read the data set into R, this is the first thing that you do, so you can visualize what the data looks like over time. And so in my program here, what I'm going to do first is open up a new graphics window. I don't have to do this. I just do this often because I want to control the width and the height. This is measured in inches, 8 inches by 6 inches, and then also my font size. So if I execute that code, a new plotting window pop up in a different monitor than the one that's being recorded right now, and there is the actual graphics window. Okay, so to do my plot, I can simply use the plot function, where with the x argument, I can simply put in, well, where my data is. It's an x. And sorry, I forgot to mention, what I did up here is I pulled my enrollment data out of OSU.enrollment and I put it into an object called x. So indeed, there it is right there. Okay. So if you've ever used the plot function, typically you also have a y argument as well. But since this is actually time series data, we don't need to do that. What R will default to is that this x actually corresponds to what will be on the y-axis of our plot. And then on our x-axis of the plot is simply like an index, an observation number, or for us, t, the time. So I'm going to put a y-axis label, x-axis label. I'm going to make the color of what's plotted red. Put a title on my plot. This panel.first argument allows me to put grid lines. The grid lines are going to be colored in gray, and the line type is going to be dotted. I'm going to remove that for now. And let's go ahead and plot. And bring up my actual plot. And here we go. So there's a plot of my data. Unfortunately, though, that's not good enough. We have these data points, and it's kind of hard to see necessarily what's happening over time. And we have some general ideas. But, what will really be helpful here is if I could, let's say, draw a line between each of these data points so that I can better see corresponding trend that may be occurring. So to do that then, that's where I can use the argument type. Type equal L stands for line. So R says, okay, what I'm going to do is just simply join each point that we had seen previously with a line. Unfortunately, though, it doesn't actually put the points there. It just has the lines. So what we can do is add the points back in using the points function. X argument, just put in X like what we had before. I'm going to use a plotting character 20. This just simply corresponds to a filled in dot. And I want the color of these plotting points to be blue to differentiate them from the red lines on the plot. So R then simply is going to add those points to the plot. And there we go. And so we can see a little bit what we saw in that table of the data. Fall's the highest enrollment, spring goes down a little bit, and then summer goes way down. And then we keep on oscillating back and forth between fall, spring, and summer for each year. We have that same kind of pattern. That pattern is what we want to take advantage of then in time series analysis, so that in the end we could forecast future enrollments. Okay. So there's a few small things that you can do to this plot as well to change the way it looks. Sometimes this may be desirable, sometimes it may not be. One thing is here, we have a way that we can actually plot both the points and the lines exactly the same time. And that is if I change that type argument from L to O. O will do both points and lines at the same time. So just to show you that indeed that happens, here we go. Now the problem though is that now the points are exactly the same color as the lines, so oftentimes I don't use this this plotting format, but obviously it is a little more convenient. Now we can do other kinds of plots as well to help us better see this trend. So once again, we know that we have this pattern. The falls are similar to one another. The springs are similar to one another. The summers are similar to one another. So how about we change this plot so we can see that trend better? How about we connect the points by semester instead of just consecutively? So to do that, then, I'm going to create 3 different objects in R. One for all the fall enrollments, one for all the spring enrollments, and one for all the summer enrollments. And to do that, I need to somehow extract, let's say, the fall enrollments from the data set. So what I can do in R is I can look at the semester variable that's in my data set and do a logical comparison. Is it a fall semester? So to do that logical comparison, I use an equal symbol there. And so what we can see here is that that first observation, which was from 1989, was a fall enrollment. So that's why R says true. The next one was a spring, so we have a false. The next one was a summer, so we have a false as well. Then the next year, fall 1990, we have a true again. And so we see these trues and falses throughout. And if I then work within my OSU.enroll data frame and say for my rows, only work with when I have trues, then what R is going to do is only return the fall enrollments. So this is the simplest, the most basic way in R that you can extract part of a data set. You use that row where you would have a row designation if you were to look at the data frame in terms of rows and columns. If that's not familiar to you, please go back to my Introduction to R set of videos. So for my rows, I just want the false. So what R is going to do is see where the trues and falses are and only return the rows that have a true. So I'm going to do that for fall. And again, we're going to get exactly the same thing there. I'm going to do that for spring. I'm going to do that for summer as well. So here's the summer. Okay. Now, let's use the plot function to first plot all the fall enrollments. So in this particular case, what I've decided to do was use the plot function. Now I will use typically the way that you do a scatter plot in R. I'm going to use a Y argument to correspond to my fall enrollments. My X axis is going to contain my times from my data frame. And I'm going to color this line in blue. I'm going to use the type equal O because I'm going to get both points and lines. And let's go ahead and do this. Also, I'm going to limit my y-axis limits to between 0 and the maximum possible enrollment that I have in my data frame. And there we go. There's the fall enrollments. To add the spring enrollments to my data set, I now use the lines function in R, where again I pull out enrollment from spring. Here's my times. I'm going to differentiate in color. I'm going to make it red. Also, I'm going to use a different plotting point. This time I'm going to use a plotting point 2, or plotting character 2. There's my spring enrollments. I'm going to do the same thing with my summers as well. And now here we can see better what's happening over time. And it seems like what's happening over time, originally the fall and spring enrollments were going down a little bit, and then they tend to go up. Maybe something similar is happening to the summer. It's a little bit difficult to see that for sure. But what this plot now, by plotting the data in like this, we can better see the trends that are occurring. And lastly, to better understand this plot, of course, it's good to have a legend on the plot so that you know what the blue, the red, and the green represent. And so to do this, I'm going to use the legend function, where for my legend, I'm going to combine together fall, spring, and summer, plotting characters corresponding to what I use here, in this case 1, 2, and 3. I use a solid line type, which is the default, which also happens to be line type equal to 1. So I have those there. I put in my colors in the same order corresponding to what is in my legend. BTY stands for box type. I don't want a box around my legend, I just want the names themselves. And then lastly, for my X argument for legend, I used locator 1, and what that's going to allow me to do is interactively click on the plot to drop in the legend. So let me go ahead and run that code, and there we go. There's my legend. Okay, so let me come over here to Word again. So we are doing a lot here with plotting. In the end, it's fairly simple. You just need to understand the code. But I want to take the time to go over the codes because simply every data set that we're going to have, we're going to do something exactly like this. And depending upon your experience with R coming into this course, you may not have seen doing plots exactly like this in the past. And to continue on this, I want to now do the same kind of plot, but now using actual dates for my x-axis. Because again, with time series data, typically we're collecting the data corresponding to a particular date. In this particular case here, we have semesters, fall, spring, and summer, but we can think of, let's say, a particular date in the fall, a particular date in the spring, a particular date in the summer when that data was collected. And putting the date now on the x-axis rather than the time index of 1, 2, 3, and so on can be very helpful in many situations. So let's talk about how we can work with dates. Working with dates in R is not always a simple thing to do, but at least for our course, I don't think we're going to run into too many difficulties. So to do this plot again, for my plot function, for my y-axis, I'm going to use this kind of a plot again. I'm going to now pull out the enrollment from OSU.enroll. I could have just simply put X there instead. Instead, I just did it this way. And then for my x-axis value, what I'm going to do is work with my dates that are in my data frame. So those are my dates. And I want to work with them in a certain format. They're actually specified as month, day, and year. And if you look at the corresponding help for the function as.date, you're going to see a variety of different date formats. And so I just had to use then the corresponding syntax then for the date format that is in my data frame. So if I just execute as.date, you can see how the data was converted a little bit to a different format. R now recognizes this actually as a date itself. Before here, R did not recognize this as a date. It was just, here's some characters that were put together. Now R recognizes this as a date. That's going to go on my x-axis. And then I'm going to have x-axis label, y-axis label, and a main title to the plot. And let me also go ahead and put the points on the plot as well. Notice in this particular case, when I'm working with the points function, I can also specify specifically y-axis, x-axis. And now here's my plot. So we have time now on the x-axis, but corresponding to the actual date. Also, if you look back at the original data set itself, we know that the dates that were used for the fall semester, spring semester, and summer semester are not necessarily evenly spread out, you could say. There's not the same amount of time between them. And by using the as.date function, R properly then represents this data on the plot by that corresponding date spacing, you could say. Now, to get grid lines on the plot, unfortunately, I cannot use this panel.first argument that we saw before, and instead I manually draw them using the AB line function. AB line function, if you haven't seen it, it's a nice function in R that allows you to draw two different kinds of lines. Let's say y is equal to a plus b times x. That's where the name AB line function comes from, but it also allows you to draw vertical lines and horizontal lines on the plot. So what I'm going to do is use the AB line function here with the V argument to say I want vertical lines drawn at these particular dates. I want to use a dotted line type, and I want the color to be light gray. Also, I want to draw horizontal lines as well, corresponding to where the enrollments are on the y-axis with the same line type and color. So that here now is my finished plot. Now, if I would have used the panel.first argument in the plot function originally, unfortunately the grid lines wouldn't be drawn properly. You can try that yourself just to see that. Okay, so now this is my completed plot. So, questions of interest when we get a data set like this. Well, what patterns are there over time? Well, we've discussed this already relative to this data set in terms of we have this, cycles every year. Fall highest, spring next highest, summer the lowest. How can I use in this dependence amongst observations to help model the data? Well, that's what we will be talking about in this course. Can future enrollment be predicted using this data? Well, from just taking a look at this, you might think, yeah, it seems that we have these trends, so we could use this kind of a data, come up with a good model to predict the future values. Now, as I mentioned earlier, most of the time we will only use the past values in our time series to predict future values. But you could also imagine particular explanatory variables that might be useful in this situation, such as, since this is at Oklahoma State University, let's say the number of high school graduates for a particular year. You could use that to predict enrollments for OSU. We will have one section of the course where we talk about this. Most of the course, though, we will not take that kind of information into account. And so again, well, why is modeling enrollment and predicting or forecasting future enrollment important? I talked about this a little bit earlier. What actually ended up happening was in 2001, the OSU administration came up with forecasted enrollments, and they forecasted way too high. This led to loss in tuition dollars from what they expected and a $1.8 million loss due to this poorly forecasted value. Maybe it's not good to say a loss because they never actually had the money to begin with in terms of these enrollment dollars. But what they had been planning on was to get $1.8 million more, and in terms of like tuition and other fees associated with students. And with OSU and with any other university that when this kind of thing happens, well, they're going to have to try to make up for it. So for example, it can result in layoffs, unfortunately. And so anyway, what then alerted me to this, what happened here was that in the student newspaper, which is called the Okali, they actually ran an article about what happened. And this is a direct link to the article. And this led me to explore further this problem. And what I found out was that the OSU administration was using rather unsophisticated methods to do their forecasting. And as we will see later in this course, if one used the more sophisticated methods that we will talk about here, they could have done a better job. Okay, so that's the first example. Let's take a look at a second example here. As I mentioned earlier, time series data comes about in many financial, business-related cases. For example, you might want to forecast, well, what would be a stock price for a particular company in the future. Here we're going to take a look at what's a common example that you see in a time series course. Rather than focus on one particular stock, we are actually going to focus on a financial index. This is the S&P 500 index. If you're not familiar with it, basically what it represents is a measurement of how, in terms of stock price, the 500 largest companies in the U.S. Are doing. And so excuse me, I should back up here. So here's my corresponding program that I'm going to use. My data was downloaded from the Yahoo Finance website. I put it into a comma delimited file. Let's see the data right. I don't have the data set open. Let me go ahead and open it. There we go. It's in a comma delimited file. I just opened it up because it was easy. I opened it up directly into Excel. And so what we have here is we have weekly S&P 500 index values, where at the beginning of the week, what did it open at? What was the high during the week? What was the low? And what was the closing value for that particular week? And that's what we're going to focus on here. So to read in the data then, I simply use my read.csv function once again. My file is specified there. Again, I need to know where on my computer that this file is located. I need to make sure that R recognizes that file directory of where to find it. So one way that I showed you with the OSU enrollment data set to find that or to set it is to use the setwd function. Another way to do this in R as well that I think it's useful for you to know in case you're not familiar with it is under File, Change Directory or Change DIR, and then you can find the actual location on your computer where that data set's located and specify it there. And now R will be ready to go to read in the corresponding data. And so let's go ahead and do that. I'm going to look at the beginning and the end of my data's frame to make sure everything looks okay. It was read in correctly. Indeed it was. Okay, so I'm going to pull out the close variable from my data frame and put it into an object called X. I don't have to do this. I just chose to do this similar to the enrollment data because, again, very often in this class we'll be working with X sub t as a symbolic form of our variable at a particular time. I open up a plotting window and then I'm going to plot my data just like what we've seen before. Let me go ahead and move this over here. I did not put the points on my plot because we have over 1,400 points and it really clogs up the plot itself. So instead I use the type equal L argument to just plot lines that connect the actual points or where the points would be. And so this is what we see here. And so we see some, again, trends over time in this plot here. Once we get past about time point 700, we can see we have a definite strong upward trend. Okay, let's talk about how we can have a more fine control of what goes on the x-axis for this plot corresponding to what we saw with the OSU enrollment data. Because this will help us make more sense or make better sense of why we see certain, let's say, dips in the S&P 500 index over time. So to do this kind of a plot, I'm going to use the plot function again, but now I'm going to use the y argument corresponding to what x is. So x is going to be the S&P 500 index value that we saw previously. And then now my x argument is going to correspond to like what we saw before with as.date, where I'm going to have that date in that month, day, year format that was in the data set or data frame as the x-axis values. I put the format argument in there to correspond to the actual format that the data is in, month, day, year. And let me go ahead and plot that and bring up the plot. And now we can see on the x-axis here actual years. Also, I'm going to use the AB line function to draw my grid lines. And here we go. So now we have a better idea of when these dips in the S&P 500 index actually occurred relative to time and events that were occurring at that particular time point. So for example, around 2008, 2009, we had this big downturn in the S&P 500 index, and that corresponds to the financial crisis that was happening around the world due to mainly because of problems with the U.S. housing market. And then we also see about March 2020, we see this large decline in the S&P 500 index, and that was due to the beginning of the COVID-19 pandemic. Okay, now on this x-axis here, you might want to have even more finer control. You might want to indicate, okay, this is actually January 2020. This is actually January 2015, and so on. And perhaps you want to put in 2016, 2017, and so on. So how can we do that? Well, we can do the plot just like what we did before, but now I'm going to add an argument called XAXT for x-axis tick marks. I don't want any of them, so I'm going to put N for no. And so what then occurs is that now on my plot, I have nothing basically as a numerical scale on that x-axis. Now I need to put it in. And the way I do that is to use the axis.date function. Side equal 1, meaning I want, there's 4 different possible sides to a plot. If you look at the corresponding help, side equal 1 is what we normally think of as that x-axis. The at argument corresponds to where do I want to put these dates. I want to put them at January 1st, 1995. That was the first date in my actual data frame, all the way up to December 31st, 2021. So that goes in my to argument. And then I'm going to go by years. With the labels that I want to use, well, I'm going to use a date labeling format. And again, a lot of this is going into nitty-gritty details for the help to figure out, well, what's the corresponding argument, what's the corresponding argument value, and so on. And so here I'm doing it by year, and also you're going to see a month. The LAS argument corresponds to the orientation on the x-axis for these dates. So I'm going to go ahead and do that. And there we go. There is now the corresponding month and the corresponding year listed as well. I can put grid lines on it on this plot too. So getting that plot perfect can actually take a lot of time. Again, as I said, you got to go through the nitty-gritty details of the help for a particular function to figure this out. I've given you some examples how to do this, but for other cases in this class, we might have to use some different arguments, some different argument names. Okay, let me come back over here to Word. So again, with this kind of data, what patterns do we see over time? Well, we see somewhat a steady upward trend, at least from January 2009 on. Could we take advantage of that then to forecast future values? Think about how that could be helpful for your own future investments if you could do that. Why is modeling the index and predicting future index values important? Well, in this case, it's money. We want to make money. We want to know what's going to happen over time. Now, the last example data set that we're going to look at is a classic. This is typically examined in every time series course. And this deals with the number of sunspots that appear on the sun. There's a number of different versions of this data set out there. I ended up going to some astronomy weather-like website, and I downloaded a new data set. This is what the data set's called. I downloaded it from this particular website here, and then the R program that I'm going to use to examine it is called sunspots.r. And what this data set gave me is the number of sunspots per year on the sun from 1700 to 2020. Let me actually show you the actual data format because it was unique. And I purposely kept it in its, you could say it's raw format that I got from the website, because you will be experiencing this kind of stuff on your own, and you need to figure out, well, how do I get this data in R even though it's not the usual comma delimited format? So while the extension on the file is .csv, which came from the website, it's actually a semicolon delimited format. And notice we don't actually have any variable names at the top of the file itself. So how do I read this then into R and get the corresponding variable names in there? Well, at the top of my program, I give you some details about what's actually in the file. I'm going to create an object called Sunspots, and then rather than using read.csv, I'm going to use the read.table function, where I specify my file, and then I specify what's separating each column of the data set, a semicolon. So SEP stands for separator. Also, I'm going to indicate what the column names are, and this simply comes from the website itself. The main thing that we are going to be interested in is the year for the number of sunspots, and the mean.total, which is the total sunspots that year. So if I read this data in and take a look at it, we can see we have the number of sunspots that appear from 1700 to the year 2020. Now, notice the variable names called mid.year. This is what what this website did. It put a 0.5 there to say, okay, we're in the middle of the year. So essentially, let's say June 30th or July 1st of the year. That's just what they use at the website. Also on the website, they report not the total number of sunspots per year, but mean.total, the mean number of total spots that were observed. So what this corresponds to, and it only occurs more so later in the data set, is that there are a number of different places around the world that actually observe or make sunspot observations. And so if you combine this information together, which what this website did, and find the mean for what each location said was the number of sunspots, that's where the mean number of sunspots comes from. We'll just call it the total number of sunspots. That will be fine. Most data sets that you will see in another time series analysis course, they won't even bother with that detail. They'll just say, okay, here's the number of sunspots per year, not necessarily talking about how that number was determined. Okay, so let me come back over here to my Word file. So I read it in, then I do a plot using similar methods to what we've seen before, and here we go. Once again, we see some trends over time. And in fact, what we have here is about a 10 to 12 year cycle for the number of sunspots that appear on the sun. Kind of a weird thing. Why 10 to 12? I don't think people really know why yet, why that occurs. Now we could also make this plot a little bit better by putting the actual year on the x-axis using similar methods to what we've discussed so far here. And so this is what I've done here. Now, I want to show you something else that you can do with this time series type of data beyond plots that can be helpful for what we will do for our analysis. This is not something that we do all the time, but it can be very helpful at times. Right now, R has read in the data, and let's see here. R has read the data in, and so the sunspots $mean.total is my yearly values for the total number of sunspots. R doesn't know that this is actually time series data, actually, but we can tell R it is by telling R, convert this to a time series class format. So the way I can do that is with the function TS. First argument, the data. My data is in mean.total of sunspots. My data started the year 1700, And then the frequency, how often did I observe this data per year, was once. So if I put all this into X and do a few different things here, suppose I look at the class of X, I see now it is recognized as a TS format, a time series format, or now knows that this is time series data. If I then also looked at what it was looking at before in terms of mean.total, before R just recognized this as numbers, a numeric format. And so if I actually type X now, and page up a little bit here, we see that X has attached some additional information to this data that it wasn't there before. It says, oh, you have a time series. It starts in the year 1700, it ends in the year 2020, and I have one observation per year. Just to show you how this TS function works, suppose instead I had a frequency of 12, and we just highlighted that. Of course, there's 12 months in a year, and so, excuse me, do that again. So now, by putting frequency equal 12, R thinks now you have time series data that's been collected over months. And so this can be a very useful thing to format your data into a particular format that you want. And then if I want to actually do a plot of the data, suppose I just work with that X argument itself. Now here's my plot with the corresponding years as well. And so there's a corresponding data for data plotted. Okay. So what are some questions of interest here? Again, what patterns are there over time? Well, it seems to be 10 to 12 year cycles. That's kind of interesting. How can we use this then this cycle, this dependence that we see over time to help model the data? Well, we'll look at models that allow us to do that. Can future sunspots be predicted using this data? It seems to be yes, because we have this 10 to 12 year cycle. And then lastly, and what's most important is, well, why is modeling the number of sunspots and predicting future values important? Well, the reason is that these sunspots seem to be correlated with the number of sun flares that occur. Sun flares are noted for disrupting communication, electronic communications here on Earth. And so if we know that, oh, we're going to have a year where there is maybe more disruptions than usual because of the historic pattern of sun flares than sunspots, we can then take that into account for communications. So that's why people are actually interested in this kind of stuff. Okay, so that's 3 in-depth examples in terms of the kind of data that we're going to be working with this semester. We'll come back to these data sets as we go along. Important things that come out of this then is understanding how to get the data into R, how to properly plot it, and there's multiple ways to do this kind of a plot, and you do need to understand the various arguments and these different ways. And then also the last thing here is understanding, well, why are we doing this? Why is this important? How are we going to, predict, forecast the future? Well, we have to understand this dependence. And that will be the subject of topics as we go along. So with that then, that was an introduction to the type of data that we are going to be examining this semester.